Okay, we are recording. We're going to talk about complex eigenvalues. How many remember complex numbers? It's maybe been a while, but you know, you have your real numbers and you have your complex numbers. So for instance, 2 plus 3 times I, that little I there, that's a complex number. Right, you have the real part. Okay, and you have the imaginary part. Well, hold on, I'll spell that right. Yeah, complex number has a real part and an imaginary part. And up to now, your eigenvalues and eigenvectors have been all real. The eigenvalues have been real, and the components of the eigenvectors have been real numbers. But now we're considering eigenvalues that could be complex. And incidentally, if eigenvalues are complex, then your eigenvectors are going to be complex as well. But remember, real eigenvectors can, well, no, we'll keep it simple. Let's keep it simple. So let me give you a moment to copy this down. Okay, so this here, what do we have to find first? The eigenvectors or the eigenvalues of this matrix A? What do you have to determine first? That's right, Mikhail, eigenvalues. And so the eigenvalues, of course, come from solving the characteristic equation, determinant of A minus lambda I equals 0. Since this is a 2 by 2 matrix, the characteristic equation is going to be a quadratic equation in terms of that variable lambda. And you can solve that, okay? You can solve that. So let's go ahead and take a look at the solution. Okay, so here's that characteristic equation. And we're going to do the determinant of that matrix. And of course, just as an aside here, the A minus lambda I would be, 1, 5, -2, 3, minus lambda times that 2 by 2 identity matrix. And that will give you what you see here. Okay. So I'm going to let you copy, but please let me know if you have any questions. Okay, I'm right here. So all right. So we get to here, all right. And incidentally, I'll just mention while I'm at it, for this fourth exam, your late homework extensions end tomorrow, right? April the 7th. Some of them will end tomorrow at 6:30 p.m. But the newer assignments you have, you'll have 2 days. Those will end on Friday, April the 8th at 6:30 p.m. So I'm trying to sort of spread out those late homework extension deadlines just to give you a little more time on the more recent assignments. And this is something that was more recent, right? So I'm trying to think, I believe, yeah, okay. So you have this quadratic equation, right? You have this quadratic equation here. And you're trying to find the eigenvalues. So this is from section 5.2, right? Section 5.2 material. You can't factor that. Oh, what formula are we using here? What's this formula that we have right here? We're solving for lambda. You know that formula. Come on. That's right, Cameron. Very good. Quadratic formula. And it allows you then to find the value, it allows you to find the roots, which are your eigenvalues. And in this case, because you have a square root, of negative 36 here, that just equals 6i. Okay? So the square root of 36 is 6. The square root of negative 36 is 6i, right? Square root of a negative number is a complex, it's an imaginary number. How many recall that from, maybe a while back? Well, all right. So, right, when Cameron and Mikhail were younger. All right, that's good. So here's lambda. Now we're going to simplify this. We should get two values. One would be 4 plus 6i divided by 2, and the other would be 4 minus 6i divided by 2. So if it's all right, I'll move to the next page to show you that. Are there any questions at all? Yes, we are going to simplify. Absolutely. Absolutely. That's right. So what I do on the next page is I do indeed simplify. And this will give us 2 plus or minus 3i. So those are your two eigenvalues. Lambda 1 is 2 plus 3i. Lambda 2 is negative 2 minus 3i. And you notice what we got here. These are called complex conjugates, right? How many remember from pre-calculus when you solve for roots, complex conjugates? I mean, when you get one complex number, you get the other one. Well, now what we want to do is we want to go after the eigenvectors. So again, the eigenvectors come from solving the augmented matrix, this augmented matrix, which I have right here. It's only, though, that my lambda is is a complex number. So let's see here. We've not found eigenvectors where the eigenvalue is complex, but the idea is the same. Okay, and we get down to here. Okay, augmented matrix, right? Get down to here, and now, well, what do we want? What do we want where the -2 is? What number do we want there? Yeah, that's right, Bellin. We want a 0. So do you remember that if you take, so you have here -1 minus 3i. That's your pivot. It's a complex pivot. And if we take that and multiply by the conjugate, and FOIL it out, well, you're going to end up getting a real number. Remember, you recall if you take a complex number and multiply by its conjugate, you'll get a real number. These cancel here, -3i and +3i. And what's I squared equal to, class? What's I squared equal to? Sure, no problem. No problem, Mikhail. That's right, -1. By definition, I squared is equal to -1. So -9 times -1 is 9, so you get 10. Well, I don't want a 10 to remove this -2 here. I want a 2, not a 10. So what I'm going to do is I'm going to take that complex conjugate, which was -1 plus 3i, and I'm going to divide it by 5. Multiply that by row 1 through row 1, add it to row 2, and replace row 2 by the result. And look what happens. So -1 plus 3i over 5 times -1 minus 3i, that will equal 2. Because the 5 divides 10 into 2. And you add that to the -2 here, you'll get 0. And also, you're going to get a 0 here. If you take 5 and multiply it by this -1 plus 3i over 5, you're going to get -1 plus 3i. And you add that to this +1 minus 3i, you're going to get 0. And that's no accident. That's no accident. When you have a complex number, you know what the conjugate is. And when you have a system of 2 equations, okay, where based off of a complex eigenvalue, the equations are redundant. They are redundant due to the fact that when you know one complex number, you know the conjugate. Well, knowing let me just put this here. This equation here, okay, that equation there, which is the quantity -1 minus 3i times xi plus 5x2 equals 0, that is the same equation as the second equation, -2x1 plus the quantity 1 minus 3ix2 equals 0. They are redundant. So you do not need them both to find the eigenvectors, the eigenvector basis corresponding, well, this eigenvalue we're working with is 2 plus the 2 plus 3i. Pretty cool, huh? It's pretty cool. So basically, you don't need to do row reduction. Yeah, you don't need to use row reduction. You have, Michaela agrees. You don't need to do row reduction here. You have equation 1 and equation 2. Both carry the same information. They're both equivalent equations, so the information is the same in both. We're gonna solve now for the eigenvector, but we need to pick one of the equations. So I personally like, well, what equation looks easier to you, the first equation or the second equation of those two? In other words, what I'm saying is, here's the one equation, here's the other equation. Which equation, both are fine, but which equation do you like better? Equation 1 or equation 2? Which offhand looks a little easier to work with? I guess it's going to depend on who you are, but I personally like the second equation more. They both look nice. Okay. Okay. Well, what I'm going to do is work with the second equation. Now, the second equation has two variables, and it's one equation. So one of the variables has to be free, right? So what we'll do, let's go ahead. If there are no questions, I'll move on here. Okay. What I'll do is I'll use the second equation, and I'm going to solve for x1. And it turns out x1 will equal the complex scalar 1 minus 3i divided by 2 times x2, and x2 is free. And we skipped section 5.4, by the way. This is 5.5, right? Okay, so we treat this problem just like we do finding eigenvectors where we have real numbers, real entries. I'm going to write out what x is. I'm going to write it out, okay? So if we go to the next page, the eigenvector x will equal x2 times the vector with entries 1 minus 3i over 2 and 1. But any multiple of an eigenvector is itself an eigenvector, so let v1 be the eigenvector with entries 1 minus 3i over 2. All right, now we're going to go after the other eigenvector, the eigenvector corresponding to lambda 2, that second eigenvalue. Lambda 2 equals 2 minus 3i. So notice that, again, the second eigenvector, 2, is 2 minus 3i. That is the complex conjugate of the first eigenvector, which was 2 plus 3i. You do the same procedure. Okay. Same procedure. And you notice I'm working this out by hand. And that's what I'm going to want you to do on your exam, right? For this. In regards to diagonalization problems. Okay, so, let me know if you have any questions. We're down to here. Okay, so are these two equations the same? This equation hold on. Dot, right? Are those two equations the same equation? Well, they are. They are, Mikhail. And you don't even need to worry about, so like for the eigenvalue 2 plus 3i, I actually showed you that the two equations were redundant. Because what happened, if we look back here, when we did the row operations, we ended up with a non-informative, the second equation. I mean, basically, we ended up with only one meaningful equation. We had two equations, right? We had two equations. Let me just read. We had this equation, and we had this equation. And we did the row operation here. And we ended up with just one meaningful equation. Okay, this one here. And so the second equation contained the same information as the first equation. And that we actually showed that. But that's going to always be true with these complex, hold on here. That's always going to be true. So let me just see here. Hold on. I thought I wrote something down here. I'm surprised it disappeared. But basically, and I should have, by the way, tildes here, right? What I'm asking is this. Can I just do this? I mean, do I need to, I mean, is it like guaranteed? Is that guaranteed? I didn't show what row operation I did, as I did with the first eigenvalue, but yeah, that's true. You don't even need to think about it. Okay, you don't even need to think about it. But you see, what you can do is if you go back to the previous step here, these two equations, they're the same equation. So at this point, all you need to do is pick one to find the eigenvector. Okay, so equation 1 and equation 2. Well, I don't know about you, but I think the second equation looks a little easier, in my opinion. So that's what I'm going to use. So, okay, here's the second equation. Here it is. I'll solve it for x1. That way I'm dividing by a real number. You could do it where you divide by a complex number. But if you divide by the complex number, then you gotta, multiply through by the conjugate, top and bottom, so that you get a real number on the bottom, right? I mean, traditionally that's what you do. Complex numbers, traditionally we like the I part, we like that to be in the numerator. So we end up getting x1 equals 1 plus 3i over 2 times x2. x2 is free. And then the eigenvector x can be written like this. And then any multiple of an eigenvector is an eigenvector. So v2 is the, I'll have it as 1 plus 3i over 2. 1 plus 3i is the first entry, and 2 is the second entry. Remember what v1 was. Oh, let's have it in blue. So when lambda 2 was equal to 2 plus 3i, the eigenvector we had entries 1 minus 3i and 2. Right? Let me just see here. That should be right. So let me just. Yeah, that's right. So look at what you have here. For the I'm sorry, hold on. this wasn't lambda 2. The first eigenvalue is lambda 1, and that was 2 plus 3i, and there was the eigenvector that went with that. Now, you're dealing with eigenvector lambda 2, which is 2 minus 3i, complex conjugate, and look at the eigenvector. Look at the entries. Compare eigenvectors v1 and v2. Are they complex conjugates too, the entries? They are. They are indeed. So that's another beautiful thing. With complex eigenvalues, once you determine one of the eigenvectors, you know what the other eigenvector is for the conjugate eigenvalue. I mean, we didn't even have to do this second part. Once we knew that v1 was the eigenvector with entries 1 minus 3i and 2, we automatically know the other eigenvector is 1 plus, has entries 1 plus 3i and 2. See that? How many think that's really cool? Yeah, it really is. It really is. So that's a nice example there. Oh, that's fine. That's fine. That's fine. Okay, are there any questions on so far on section 5.5? We're going to take a little break here, but are there any questions? Okay, good. I'll stop the recording.